All right. Today in class, we studied pendulums and the effect of the length of the string of the pendulum on the period. And the period is defined as the amount of time it takes from the moment you release the weight at the end of the pendulum until it comes back to where it began. So it swings and then swings back. That's one cycle, and we call that the period, measured in seconds. So we had 5 different groups do it. Their data can be seen in the upper left-hand corner. X values are string length and measured in meters, and you'll see the purple dot, which is Y2, the Y2 column, and that was the period, the time period. So it might not look to be a square root function, but indeed, if I turn on the red line, t equals 2 pi times the square root of L over G. So we've got the Earth's gravitational field strength input for G. Obviously, that would be different if you're on a different planet, and the pendulum would swing, for example, very slowly on the moon. But we're using 9.81, 2 pi is a constant, so the only 2 variables are period and string length, L. And Desmos just kind of knows that t is on the y-axis based on how we have written the equation, kind of in y equals form, which is pretty standard. So it knew to graph it the way we wanted, and then you can see the data passes through all the points that were collected except for one. So maybe one point was just a little bit off in terms of how the period was measured, or maybe how the string length was measured. But it really matched up well for 4 of the 5 data points. So that just shows right there that the relationship between period and string length is a square root relationship. Now, the question is, what can we do with that? Well, first of all, the square root function has many slopes, right? The slope is continuously changing. What we want is to, because this is an algebra-based course, is to find a way to graph period versus string length such that we get a linear equation. And one way you can do that is by graphing t squared. So I'm going to turn off y2, and if you look at the y1 column, it's the same values as y2, except they're now squared. And if we take a look, zoom out a little bit, you'll see that the green dots form a straight line. Well, 4 out of 5 of those points do, and if we turn on this equation, y equals mx plus b, which is our standard form for slope-intercept form, we can see that the slope of the line is 4.1. Now, great. What can we do with that information? By the way, right now I should change the title of the graph to period squared, because technically we're not graphing period, we squared it, and then it would be measured in seconds squared. So that would be seconds, and then we would use the little caret, which I am not seeing. Oh, there it is. Seconds squared, right? Because seconds times seconds is seconds squared. Okay, so now we have accurate labels on both the y and x axis. Now the question is, what can we do with that 4.1 value, right? Just because we graph t squared versus L. Well, let's take a look at what we can do with that value. We'll jump into notability, and remember that our slope was 4.1. So let's start a new equation. Here we go. Let's get organized. All right. So we remember the slope of the graph was 4.1, and that was a graph of t squared versus string length L. So the physics equation relevant to this situation is t equals 2 pi times the square root of string length over field strength G. This is true for all pendulums. Notice mass does not have an effect on the period at all. It's purely based on the string length and the gravitational field. Well, this graph over here is t squared versus L. So we're going to manipulate this equation so we get t squared. So on the left side, we'd have to square t, and on the right side, we'd have to square the entire expression. So inside the parentheses, we have a lot of parts being multiplied, factors being multiplied together. So you get 2 squared times pi squared times the square root of L over G squared. I'll go ahead and write it out for now. Square root of L over G squared. So notice the 2 has been distributed, the exponent has been distributed all factors. So let's clean it up. Here we go. T squared equals 4 pi squared, and the square root of anything squared is that thing. So you end up with L over G. Okay. Now I'm going to rearrange the equation a little bit. Because we graphed t squared on the y-axis and we graphed L on the x-axis, I'm simply going to rearrange this as t squared equals 4 pi squared divided by G times L. I did not change the right side at all. I just simply moved the location of the divided by G. But the value of the expression is exactly the same. So what do I have now? Now I have an equation that's in the form y equals m times x. We could add the plus b and write it plus 0, right? Because then we're not changing the equation. So our y-intercept would be 0. But what we care about is the slope, which is, oops, I forgot my little squared term, which is 4 pi squared over G, right? So notice I'll use multiple highlighters. So t squared was graphed on the y-axis, and length was graphed on the x-axis. So the coefficient of the length is this expression 4 pi squared over G, and we can simply set that equal to our value for m that we got on our graph when we graphed our points of t squared versus L, and that was 4.1. So we're gonna set this expression 4 pi squared divided by G equals 4.1. All right, so we just set these two expressions equal to each other and replaced m with 4.1. And then we can solve for G. So if we multiply each side by G, I'll go ahead and show all my math here. All right, and then divide each side by 4.1. 4.1, right? The G's will cancel, the 4.1s will cancel, and we get G equals 4 pi squared divided by 4.1. And now I'll pick up my calculator and I'll carefully type in sorry, we've got some technical issues on the other end here. You probably figured out by now the value before I did. Sorry for the suspense. 4 times pi, I'm old school with my calculator here, times pi again, divided by 4.1, 9.62. 9.6, I'll just say 9.6, and that's G, so that would be newtons per kilogram, or meters per second. Meters per second squared, yep. All right, so there we go. Now, we should be getting, right, if all our data was perfect, our measurements were perfect, everything, we should be getting 9.8 newtons per kilogram as a value of G, but it's not too shabby. We're probably within, we're only a couple percentage points off. So that's what you can do when you graph, when you linearize your data. You can actually use the slope, because there is now a single slope value, and set it equal to an expression. The other thing we did in class was, instead of t squared versus G, right? So there was two ways to linearize the data. You can do t squared versus G, or you could do t versus the square root of G. And that also would give you linear data, just a different slope. Okay, so I'll just show you that. I'll show you those data values. So we graph those down here. So if we're on the x-axis, I'm sorry, square root of L, not square root of G. On the x-axis, we graph the square root of L, and on the y-axis, we just have T, right? And there's our data, and it is a different slope value. Go ahead and adjust it here, and you can see it's closer to, let's try to get somewhat precise, 2.1. Yeah, I'll say right around 2. Okay. And then if we do the math to figure out, let me clean this up a little bit. Sorry about that. This was L, and this is the square root of L. So similarly, we could figure out the meaning of the slope by starting with T equals 2 pi times the square root of L over G, and now rearrange the equation for T versus square root of L. So let's take a look at what the math would look like there. So we have T equals 2 pi times the square root of L divided by the square root of G. So that's just using some math. You know, this term right here can be broken into 2 parts. It's just a square root rule. And now I'm going to rearrange the equation. I'll say T equals 2 pi times the square root of G times the square root of L. All right, so now we again have the expression y equals m times x. So just check it because we graphed the square root of L on the x-axis, and we graphed period on the y-axis. So this expression right here is our slope, right? So when I think it was 2, so if we set 2 pi over square root of G equal to m, right? But we know the m value is 2, so we can replace m with 2. And then we have 2 pi over the square root of G. And let's go ahead and solve for G. We should get 9.8 or something close to it. So let's do some flipping here. We'll say 2 pi divided by 2 is equal to the square root of G. Basically, I multiplied each side by root of G and divide each side by 2. 2's cancel. This is really interesting. G is equal to, we'd have to square each side, and we get pi squared. Wow, that is really cool. That just kind of works out because our slope was exactly 2. It's probably not exactly 2, but it's close to 2. Well, what is pi squared numerically? Let's figure it out. Clear. Pi times pi. 9.87. 9.87 newtons per kilogram. That's pretty awesome. So very, very close to 9.8, the actual value of G on the Earth, at the surface of the Earth, I should say. So there you go. 2 different ways to linearize data when you have a square root function.